Hello everyone, welcome to the Electromagnetic Spectrum Lab channel. In this video, I am going to talk about a significant effect in the multi-quantum well structures that called band non-parabolicity effect. Let's learn more about it. In general, for semiconductor heterostructures with relatively low barrier heights and low carrier densities, the carriers cluster at energies near the conduction band edge. For example, within a couple of 100 millielectron volts compared to a band gap of the order of 1.5 electron volt. In this region, the band edge can be described by parabolic EK curve as this shown equation. However, in situations where the carriers are forced up to higher energies, either by large barrier heights and narrow wells or by very high carrier densities or high temperatures, the previous equation is only an approximate description of the carrier dispersion. This is especially important for holes in the valence band. The approximation can be improved upon by adding summation terms into the polynomial expansion for the energy. For example, no matter how complex the band structure along a particular direction, it clearly has inversion symmetry and hence can always be represented by an expansion in even powers of k if sufficient terms are included. So the energy E can be described by this series. Usually, when discussing single band models, as has been focused on entirely so far, the energy origin is set at the bottom of the band of interest, and thus A0 is equal 0. In addition, truncating the series at k power 2 gives this relation for A2 coefficient. So by these explanations to include terms in k power 4, hence accounting for band non-parabolicity as displayed in dispersion diagram in this figure, the best approximation is this relation. Using the basic definition of effective mass, unlike the case of parabolic bands where effective mass is a constant, it is a function of k, then it is also a function of energy. So after some manipulations, band non-parabolicity is accounted for by an energy-dependent effective mass as this equation, where V is the band edge potential, M star 0 is the effective mass at the band edge, and alpha is the non-parabolicity parameter, which is usually greatest when the band edge under consideration is close to other energy bands in the material. Precise values of alpha may be obtained experimentally or extracted from more detailed models of the band structure. However, simple approximations exist near the edge of the conduction band, such as that given by these relations. The second expression can be used to estimate the significance of non-parabolicity in a range of different materials. It is worth noting that although non-parabolicity may be very significant in narrow bandgap semiconductors, it can be ignored safely for low energy electrons in many common materials. By applying energy-dependent effective mass, Schrödinger equation can be written as this expression. By discretizing the typical Schrödinger equation with constant effective mass can be expressed in matrix form as this equation, which H is a matrix containing all the related coefficients. Incorporating band non-parabolicity into matrix methods is unfortunately more complicated than with the traditional iterative method, because the energy appears within the coefficient matrix. This means that the matrix no longer contains constant coefficients and is instead a function of energy. As such, becomes a nonlinear eigenvalue problem which cannot be solved directly using the rapid methods. Solving such a problem needs nonlinear algebra operation. By rewriting this equation for Schrödinger equation with energy-dependent effective mass, the H matrix can be expressed as A0, A1, A2, and A3 matrices that are multiplied by different power or energy parameter and build a nonlinear eigenvalue problem. One tool to solve this problem is Computational multiphysics package, which uses an algorithm that is capable of solving eigenvalue problems which are nonlinear with respect to the eigenvalue. In the next videos, I will show a simulation setup which solves the Schrödinger equation with energy-dependent effective mass for multi-quantum wave structure. In review, I introduced the band non-parabolicity effect in semiconductor heterostructure. I explained the energy-dependent effective mass approximation and the challenge to solve the related Schrödinger equation. I hope this video can be helpful to you. I would be grateful if you could subscribe to my channel and like and comment on the videos. Good luck and have a nice time.